record. Go. Go. All right. 3, 2, 1. Take 3. Let's turn the arc reactor back on. Oh. Did it just turn off? Oh my goodness. What's going on? Okay. Try this again. I like it turned more this way. Yeah. That's good. Okay, we are recording, so let's go ahead and start. Welcome to Quantum Kinetics Corporation. I'm your host and CEO, and today we're going to be talking about the Arc Reactor emissions running on a 12-volt battery out in the wilderness, and you can check out that video in the link description. We did a demonstration of the Arc Reactor running on an inverter off a 12-volt Vmax battery. So we were able to sustain over 130 million degrees Celsius, which essentially is 11.6 to 11.4 keV emissions for 60 seconds. Now, I'll remind you that the Arc Reactor Fusion on Demand technology can hold sustained nuclear fusion for days, weeks, months, and even years. This technology is reliable, safe, and consistent. We'd like to direct your attention now to the emission spectrums on the screen. So, what we're looking at here, these peaks, these blue peaks, are the arc reactor. What you see here on the bottom, this little tiny red emission, that is a calibration sample of iron 55. That is an actual X-ray emission of beta decay of atoms that are unstable, that are going through some type of electron capture event. And the arc reactor also does a very similar phenomenon called electron capture using synthetic gravity, also known as negative differential pressure. We like to call it safe nuclear. Also, we like to call it quantum kinetic well phenomenon. So we're going to look at the spectrum here, and this is an 11.27 keV emission. The next one is a 9.35 keV emission. This one down here next to iron. So what this tells you, ladies and gentlemen, is that the ambient air, and by the way, this was not in a vacuum chamber. It was out in the wilderness, and it was just on a sunny day. And you can see that the ambient air itself actually has a characteristic peak. So that tells you that there's some very dynamic nuclear processes occurring with just ambient air. It's almost as if the air is trying to turn into some type of iron oxide. Now, the next peak, which is really interesting, is around 3.9 keV, and then there's another peak right here next to it at 3 keV. It's very fascinating because there is an emission spectrum at about 3.55 keV, which some speculate in the astronomy field that there is a antimatter stimulation at 3.5 or somewhere around there. And this reactor instantaneously tickles positrons and also electrons. And so this patented, trademarked, and copyright protected technology is proving that we can do transmutation. We can reduce uranium-235, 238, and 234 by 80% in 24 hours. So an only way to do that is to create some type of negative differential pressure that stimulates negative pressure on the positrons. And we'll also show you some emission spectrums of that with the raw data as we go further into this. The highest peak is about 1.1 keV, as you can see here. And what that tells us is that the arc reactor is essentially causing electrons to swirl down inside the reactor. Then the transmutation takes place. This is called Bremsstrahlung radiation. And some people say, yeah, Bremsstrahlung only happens when you're accelerating electrons. That's actually false. Electrons can actually give off X-ray radiation when they're slowing down. Anytime you agitate or move an electron in its non-vectored path, it will get angry and it will emit an X-ray. And these other higher peaked X-ray emissions, these ones are telling us that the atomic structures are either turning into, this one would be about a carbon or a nitrogen. This one would be a lot heavier elements as well. So these characteristic peaks at room temperature, running around 5 watts of energy input from a 12-volt battery, this is definitely sustained nuclear fusion. It is reliable, it's affordable, and it's robust, and it's compact. This is really the nuts and bolts of what nuclear fusion is supposed to look like. And here at Quantum Kinetics, we love showing our data because it's good. Okay, so the next thing we're going to look at is we're going to look at the history. What this tells us is that within each peak here, that's the total count per second. And so as you can see, there's these kind of undulating peaks and troughs, and they're actually, you can kind of see a little bit of an AC wave forming inside there. That is characteristic of stars. Stars have this thing that basically they swirl and they pulse and they resonate. And this is what you're seeing here. This is also in science, they call this mode locking. It's what happens with lasers, and it also happens with planets, stars, and other constellational objects in outer space. So the Arc Reactor not only has a similar characteristic emissions of nuclear fusion and also suns and stars and black holes, but it also has the pulse frequencies of the counts of ionization or transmutation. The next thing we're going to look at is the rise time. Now, what this tells you, ladies and gentlemen, is the rise time is in microseconds, and this tells you what kind of radiation signature this is. And just to give you a little bit of a historical context, the Muon Catalyzed Fusion that was done way back, I think it was in the 90s, I believe, somewhere mid-90s, by Luis Alvarez. His muon fusion process, bubble fusion, could only do about 2.2 microseconds. And essentially what that meant is that it wasn't really useful for industry, though he got a Nobel Prize for doing actual fusion in his chamber, but it never really amounted to anything because it really wasn't that helpful. It wasn't at industry level. Now, if you look at our screen here with the Arc Reactor, you can see that the rise times are much larger than the 2.2 microseconds of bubble fusion, which tells you that our rise times are in the same vicinity as an iron 55 trying to turn into manganese. You can see the red here. So what that tells you, ladies and gentlemen, is that this is happening very often, it's happening very frequently, and it's a very consistent rise time photon emissions, which is really exciting because if you look at the number of occurrences, you can see per second that we're getting about 120,000 at the lower range, and we're getting up to the 35,000 per second on the 13.7 microsecond rise time, which that tells you everything you need to know about these types of photons, that they're very consistent and they're very reliable and they're very powerful is what that tells you. So we're going to move over to the actual raw photon signatures and it's determined by the millivolt action. Basically, a voltage is 1 through 3 electron volts. Essentially, is visible light. And if you look at these emission peaks and these vibrations, typically a normal photon will only go positive, and then it will come back down to zero reference. But as you can see here on these pulse sequences, that we're getting not just positive pulses that go up and down, but we're also seeing photons that actually rise from ground state, below ground state. And this is happening continuously, like all the time in these beats. And this is really exciting because what this tells us is that this is actually turning on fusion, and then it's going back to normalization background, and then it's turning on fusion again. What these photons tell us is that there is a basically particle oscillation as an energy generator. And by the way, that's a trademark thing. What we're doing is we're agitating the electrons back and forth at such a rapid pace that the agitation of the antimatter comes too with basically in this process. And we really are excited about this technology because one, we've mentioned this before, it's patented, trademarked, and copyright protected, and we are ready for industry. And by the way, there are no other fusion companies that can say that they're ready for industry. We are beyond research mode. We've spent almost 10 years doing it, and now it's time for us to show our cards. And we're so happy to show our cards because our cards are double aces with 2 aces on the flop, okay? So yeah, in terms of poker, we pretty much won this race, and that's why we say first diffusion, because we actually do have nuclear fusion. So and then we'll go to the summary, and as you can see that we did a background radiation check, which is the first one, B1, and there was no radiation. And by the way, this was outdoors. And then we turned it up a little bit to 10 volts, and then we turned it up to 30 volts, and then we did 25 volts for the final test that you guys can actually check in the video in the podcast episode 2, which are first diffusion. So essentially that's it. That's the overview of what we were looking at here with the Arc Reactor using the XR100CR X-ray detector using Amtech technology. And we're very excited to, oh, and by the way, we were running the Arc Reactor 11.6 kilohertz with a 10 hertz gate. So just so you know, that's what we were doing there. Is there anything else I want to talk about? I don't really think there is. That's pretty much it. So anyway, thank you for tuning in to the analysis of the Arc Reactor's 12-volt demo of sustaining safe nuclear fusion on demand. We are super excited for you guys to subscribe and check out our content. And we're looking forward to ushering in a very new future for the human race. And remember, truth is stranger than fiction. So I know it may seem like a really heavy pill to swallow when you look at this stuff, but believe me, when we started doing this too, we were like, whoa, this is crazy. But every single test we've ever done has come back positive, and we're just so thrilled that we're able to legalize the technology and get this out to the world and let you guys know that quantum kinetics is the first diffusion, and we are so excited to show you. So stick around. We got some really amazing stuff coming. We've got a really big surprise for you guys coming June 28th, actually. And so we'll announce that, and we're really looking forward to the future, and come along with the journey with us. And anyway, without further ado, I'll let you guys go. And again, if you have any questions, go ahead and hit us up in the comments section as well, and we'll talk to you soon.